You're the vision manager for imaging and this is such a hard word in English. Spectroscopy. Now I have it. And Thorsten, you're going to speak about imaging cameras for quantum phenomena. Tiana's helping with the presentation, and then we can say stage is yours.
Thank you very much for the introduction. My name is Thorsten Pieper. I work for Quantum Design, a company distributing scientific equipment. We are located in Darmstadt, and we are representing plenty of manufacturers of scientific equipment, and some of the logos you see here on the screen. I'm the division manager for the imaging and spectroscopy department. And in this role, I represent mainly two companies. The first one is Advacam from the Czech Republic, producer of X-ray cameras and X-ray detectors, mainly used in synchrotrons and X-ray tomography apparatus. And the other company is Andor Technology, under the roof of Oxford Instruments. The cameras that I'm going to talk about today are made by Andor, and many of them are used in ion trap experiments that you have seen in other presentations today. We are also responsible for 3 other camera manufacturers like AOS, Cordin, and Xenex. And these camera manufacturers make cameras especially for NIR, near-infrared imaging, and for high-speed applications. The idea for today's presentation was to present basic quantum phenomena that some of you have already seen in the university or even in school, and associate these experiments to a certain type of camera. I'm going to talk about 3 basic concepts of quantum phenomena. One of them is today called quantum simulation, with focus on ultra-cold ions or Rydberg ions. The second one are quantum gases. And the third one are experiments with entangled photons. And for the reason of understanding, I'm going to start with entangled photons. The cameras that I'm going to associate with these experiments can be based on different technologies. Many experiments require very sensitive cameras, and other experiments require higher resolution or smaller pixel sizes. There are many features of cameras that can be relevant in these different experiments. And I'm going to show the one that I would choose as a sales engineer and that I typically recommend for certain applications. So as a motivation for today's talk, I want to start with Young's double slit experiment. It's very famous, and the concept is shown on this slide. We have got a source of photons at the bottom of the slide. In the center, you see a double slit, and at the top, you see a screen which shows interference fringes. The classical explanation for this experiment is that what we observe is interference of light waves. But now imagine that you reduce the intensity to the single photon level. In this case, we cannot use the explanation from classical physics because it is not complete. We need a different explanation, and quantum physics provides us with a better explanation for the result. Even in the case of having single photons, we see an interference of wave functions rather than classical light waves. And it is essential for this experiment that the stream of photons is so small that the single photon can choose between the left or the right slit. And the quantum physical explanation exactly applies in this case. Surprisingly, we get the same result performing the experiment with high intensity and with low intensity. And a variation of this experiment has been done by these three guys, Mr. Aspen, Paget, and Spalding. What we see here is a non-classical photon source in the form of a laser and a nonlinear crystal. This nonlinear crystal generates a pair of entangled photons, of which one of them goes to the right and is detected by a single point detector. This arm of the experiment is called a heralding arm because it provides a trigger signal for the camera, which is in the other arm of the experiment. And the object that is observed is in the signal arm, just in front of the camera. And by triggering the camera, you can choose only photons that are entangled with the heralding arm. Other photons will be ignored. And if you put a double slit in the signal arm of the experiment, you can generate a double slit experiment with a coherent source. Coherent means that single photons, a stream of single photons is detected rather than a wave of light. And in this video, we should see, yes, it does work, we should see the interference pattern slowly developing by detecting single photons. This will just take 10 seconds to see. You see already the expected result, the same interference pattern that you get with a classical source of light. So how are entangled photons generated? I mentioned already that you need a laser beam with a monochromatic wavelength and a nonlinear crystal. The physical process that occurs in the nonlinear crystal is called spontaneous parametric down conversion. In this process, you generate, from a single photon, you generate two resulting photons that can have the same wavelengths, but do not have to have the same wavelengths. What you see here are two cones of light with different polarizations. And at the intersection of these cones, you can find two entangled photons with different complementary polarization. They are either horizontally or vertically polarized. And these entangled photons can be used in two different concepts of imaging. I call the first one ghost imaging and the second one coincident detection. The next experiment is an example for ghost imaging. The experiment was carried out about 10 years ago by Gabriela Barreto-Lemos from Professor Zeilinger's group in Vienna. The paper she published is called Quantum Imaging with Undetected Photons. And in this slide, I present the setup. Again, we have a source of photons from a laser. In this case, a green laser with 532 nanometers was used. And the laser beam goes through a beam splitter to a nonlinear crystal. In this nonlinear crystal, we generate a pair of entangled photons with different wavelengths. That is very important. We have got one photon with 810 nanometers and a second photon with 1550 nanometers. The key of this experiment is that the detector, the camera that we have chosen here, is only sensitive for 810 nanometers, but it is completely insensitive for 1550. So there's only one path where the 1550 nanometer photon travels through the object. That's shown in the center as a shape of a cat. This is the object of interest that should be examined in this setup. However, the camera that is used as the detector is completely insensitive for this light. The camera on the right side of the experiment can only see the yellow photon with 810 nanometers. So how can it be that we still get an image of the object? The photons have never seen it. And this is a typical example for quantum physics in action. Due to the fact that these photons were entangled, they carry the same information. So those photons that have passed the shape of the cat transfer the information to the entangled photon in the detection arm. And so the camera does see the object using photons that have never traveled through this shape of the cat. It is very essential in this experiment that there is not a single source of photons. In this type of experiment, we need two sources of photons, and so the photon can travel two ways. And it is essential that the observer does not know which way the photon takes. And that is why you see here two nonlinear crystals in the setup. In this type of quantum optical experiment, we do not need a heralding photon. There is no trigger. And this is because we are observing a static scene which does not need any time resolution. And for this reason, we can use almost any camera for this experiment. This is different in the next experiment that I present. I don't want to forget to mention that the concept of the experiment can be very practical, can be practically used in medical physics, for example, for diagnostics of tissue that is normally intransparent for visible light. And in this paper, we see an example for this ghost imaging method with undetected photons applied to a certain tissue that is transparent for infrared light, but not transparent for visible light. But a visible camera was used as a detector here. So relevant camera features for this kind of experiment can be many. And as I said before, for a static scene of imaging with undetected photons, we can use almost any type of camera. It can be EM-CCD, CCD, or a CMOS camera. And relevant criteria to choose can be the quantum efficiency for detection, the resolution, the dynamic range, or the frame rate and read noise. In other experiments, we will see that certain features are extremely relevant. For example, the next one. The next type of, or the next class of experiments I call coincident detection. In coincident detection of entangled photons, we generate a pair of photons again, and we have two arms of the experiment. One of them makes use of a single photon avalanche photodiode on the left side. This is the heralding arm of the experiment, and this gives a trigger signal to the camera shown on the right side. In this case, we need a camera with high time resolution. And one example, again, is from the laboratory of Professor Zeilinger in Vienna. This experiment was also done almost 10 years ago by Robert Fickler. And in this variation, a hybrid state is created, a hybrid state of two polarized photons, and one of them additionally carries spatial information. This spatial information is imprinted on the second photon by using a spatial light modulator. And in this case, we have one heralding arm carrying only information about the polarization, and a second arm carrying polarization and spatial information. And using this type of setup, we can observe real-time imaging of quantum entanglement. The results are published in this paper from 2013. And depending on the polarization, the observer can choose any direction of polarization, and according to this, a certain spatial pattern that is generated on the other photon. There is a video on YouTube showing this in live and in real time. One could imagine that for this type of experiment, a high quantum efficiency on the camera side is essential. In fact, it has shown that the quantum efficiency here is less relevant for the result. In fact, the experiment was carried out with 810 nanometer photon, probably, or quite long wavelengths. And the quantum efficiency of the camera was only 3%. It still works, because there is a feature of the camera that is extremely relevant here. We need a camera with spatial resolution and high time resolution in the range of nanoseconds. This feature is called optical gating, and it is only available in intensified cameras, a combination of traditional camera with an intensifier. These cameras are fully integrated and produced by Andor technology, and they are called Andor iStar camera. They give us nanosecond time resolution and the possibility for synchronization with low latency and low jitter. This is required to capture the photon that was heralded in the second arm. So let's go to the second class of experiment, which are quantum gases. Quantum gases are examined since 20 years, probably. I would describe them as a new form or new state of ultra-cold matter. Quantum gases can be made by several different species. What I mean by that is special chosen elements like cesium, rubidium, dysprosium, or strontium. And in optical traps, they can be cooled to extremely low temperature. They must be cooled to extremely low temperatures to form this Bose-Einstein condensate. As an example, I show results from Tillmann Pfau's group in Stuttgart. They provided us with this image of a Bose-Einstein condensate made of dysprosium atoms. And this cloud of atom can best be observed by a method called absorption imaging. Oh, I'm already late. So the camera that we have chosen for this experiment is a camera that gives us high dynamic range, good resolution, and high quantum efficiency at 421 nanometer, because this was the chosen observation wavelength for this element. This is the quantum efficiency diagram for these cameras, and I have marked the 421 nanometer with an arrow here. This is an Andor Ixon EM CCD camera, which is state-of-the-art for this type of experiment. It allows to acquire absorption images in a very short sequence, in a mode called fast kinetics mode. And this gives us a very high time resolution for a short sequence of images. For this type of absorption imaging, typically 3 images are required, but they have to follow in a very short time. So this type of camera is the only one that can achieve a time resolution of less than 300 microseconds for a full image, almost. And that is the main reason why we chose these EM CCD cameras for Bose-Einstein condensates. The last experiment is called quantum simulation, and we have seen several of these experiments here in ion traps. It looks very similar, but in fact what we see here are not clouds of atoms, but we see single ions trapped in Paul traps, for example. And they are magnified by objective lenses and then imaged on a sensitive camera. Again, we can choose between different species and different observation wavelengths. In this case, we see a linear Coulomb crystal of 10 ytterbium ions, and they are detected at 370 nanometers. And these nice images were provided by Tanja Milchtäubler from PTB in Braunschweig. And she has got several of these cameras for experimenting with optical clocks, for example. And criteria for choosing the camera are, again, high resolution, high quantum efficiency, high frame rate, the possibility for photon counting by thresholding, and last but not least, the possibility to establish real-time control. This is very hard to achieve with slower cameras or cameras working with USB interfaces. These EMCCD camera have a special interface that can be used for low latency real-time experiments. And that's the reason why most users decide to use these Andor Ixon EMCCD cameras for this purpose. That was the last slide, and I hope I have not expanded.
No, Thorsten, thank you so much. Thank you so much. We are good in time. We have our next speaker waiting. I would say let's have the one-on-ones for questions at your quantum design stand, so we're not falling behind in the time. You said like it's right here?
Yes,
on the left?
And we are standing here at the left side,
And
just next to the truck.
Perfect, and you're going to be here until 5?
Until 5.
Perfect. So, thank you very much, Thorsten, for that overview.